Hello, everyone. Very, very nice to be here. As Susanna mentioned, my name is Haze Núñez. I am a sixth-year PhD candidate here at Caltech in their astronomy and astrophysics option, and I have the pleasure of being able to share with you all what has been a pretty productive and very interesting thesis. So there will be lots of different points of introspection here, as sort of implied by the title, looking inside and out, and I'll talk a little bit more about what that's supposed to mean. Quick little introduction about myself. I was born and raised in Southern California. All my family's from Compton. I myself grew up in like Carson and Torrance, so like all within 15 minutes or so of the area. I went to Cal Poly Pomona, where I did my bachelor's in physics with a specialization in astrophysics. Before that, I was at El Camino College, 45 minutes down that freeway, which is a community college where I spent 3 years there, and now I found myself here at Caltech. Can't seem to leave SoCal. It's kind of nice here. One other cool thing about me is that I've been I guess, I don't know what the best word to use here, but I've been involved in BSEC since my first year as a grad student. So as I mentioned before, I'm a sixth year, and I've been, I was secretary for like my first 3 or 4 years. I was co-president for a year, and it's been incredible to see the amount of growth that first off the Black community has had here at Caltech, and then just the organization as a whole. The BSU, which is the undergrad version of BSEC, did not even exist because we didn't have enough critical mass to do that. So it's phenomenal. I just want to highlight two contributions during my time here that I think are worth noting. The first here is highlighted by this picture in the center showing me and two other graduate students. When I was admitted, I was actually one of 5 Black grads that were admitted my year, and there are only about 11 or 12 Black total grads in all of Caltech, which is pretty wild to think about. And we pushed during, this is the wake of the George Floyd riots and the unjust murder, for Caltech to be a lot more equitable and anti-racist for all students, but especially the Black community. And I think that led to a lot of stuff. And I think the most important thing was just institutional buy-in, that this is actually worth the time. The second thing is the inaugural CBAS conference. So I was one of the cabinet members and co-president for that. So I don't know, it's just nice to be here, and it's very nice to see all of this amazing stuff. I always show this slide to astronomers to convince them to get rid of ego. I don't think I necessarily need to do that for this audience, but I do want to give a highlight to two folks who are very important to who I am now as a result. Dr. Lisa Townsley and Jose Flores Velasquez on the right here, who we lost during my PhD. I think they both taught me that you can be both a good scientist and a good person, and that should be the goal at the end of the day. All right, so this is an astro talk. So Sheena did a pretty good job, actually, of explaining the main core of what I'm going to be talking about today. But this is a starburst galaxy that's nearby called M82, the 82nd Messier object in its catalog of non-comets. It's a starburst galaxy, but I want us to focus on sort of 3 different components. The first here is the interstellar medium. So all of the objects and the black holes that Sheena was talking about are all basically in here, in the interstellar medium. Interstellar means in between stars, and medium in this case is just visible matter. What you notice about this galaxy is all this red stuff. So these are galactic outflows. It's actually ionized hydrogen. We can actually see this with if you have the right filter and if you have deep enough skies. But these are galactic outflows. And this is a starburst galaxy, so you have a bunch of star formation that's in the core of this, or basically near the core of the galaxy, and they're deriving these huge flows of mass. That mass has to go somewhere, and it goes into what we call the circumgalactic medium, the CGM. And so this is going to be the core of this talk, this interplay between the ISM and the CGM. Now, I think another good question to ask is, well, why? Like, what's the core of my thesis? Well, the core is to basically account for the circumgalactic medium in our understanding of galaxy evolution. And specifically at a time in the universe's history, when galaxies were forming stars just about as quickly as they can. If you sort of look at an optimization curve, it's exactly at the peak, which is why it's called cosmic high noon. So it turns out that we've learned a lot about star formation and the interstellar medium. It turns out that it's actually very complex. I'm showing a movie of our current state-of-the-art understanding with as many physics models as we can applied. What we're showing here are, the colors here are over densities, and over time, I'm gonna actually move this forward here. You'll start to see some stars form. There you go. What you notice about this process is that it's very messy. There's nothing that's very homogeneous about it, right? And then over time, once you start to have protostars forming, you have these jets that are shooting up and down. So this is actually a result of mass that's accreting onto the central source, interacting with the primordial magnetic fields of the star, basically ejecting this material. This is very, very state-of-the-art. It's called Starforge, made by Mike Grudich. And I think a good question to ask is, do we actually see this? And the short answer is yes. This is the Carina Nebula. This is the first region that I actually wrote a paper on. And what you can see is very, very similar to what we saw in these simulations, which makes sense, right? Like the simulations should be depicting what actually happens in nature. Well, what about those outflows? Turns out that yes, this is exactly what we see as well. These are huge, giant molecular outflows that have a pretty important impact on the mass of the star that you can actually get to in the local universe. And for those that are curious, what this actually looks like in the research context is you want to take a look at these very large populations of stars. So this is also, again, the Carina Nebula in the first paper that I ever wrote that I finished as a grad student, where I was looking at, the X-ray emission from these very, very young stars, which is pretty fun. So even though the ISM is very complex, it turns out that if you sort of average over the entire interstellar medium, things look kind of similar regardless of what galaxy you're looking at. It's actually one of the more remarkable parts of astrophysics, that you can just look at a random sample of galaxies and you can actually start to see scaling relations between, for example, how many young stars that exist within that galaxy and, for example, the color of that galaxy. In this case, color is just the flux between different filters. What we ended up finding out after looking at very, very large samples of galaxies is that galaxies seem to be missing mass. So one thing that I forgot to mention in the previous slide is that when you look at galaxies, what you're really just seeing is the interstellar medium because it's very dense, so you have a lot of photons that are being emitted. And once we looked at a very, very large sample of galaxies, this is back in the early 2000s, this is looking at the observed mass versus the true mass, one would expect, if everything was working the way that it should, that all of these colored points here should follow this line here. This is basically the theoretical expectation for the amount of mass that you would expect to see. But as we can see, even if you go to where the Milky Way is, we're actually seeing about maybe an order of magnitude less at every single mass, which is interesting. What this implies, and there's lots of other lines of evidence, but I think this is the most clear to show, is that there exists some reservoir of gas that surrounds the galaxy, what we call the circumgalactic medium. And therefore, the physical processes that govern it must be fundamental to how galaxies evolve over time. One of the things that we found out ever since was that the galactic ecosystem appears to kind of be similar, or at least analogous, to the water cycle on Earth. So in particular, if you want to follow where the majority of water exists on Earth and what's going to happen, you need to basically account for all these processes: collection, evaporation, condensation, and precipitation. In other words, the water cycle is vital for water and life on Earth. Analogously, for galaxies, you have what's called the baryon cycle, where in the same way we have the interstellar medium here that's driving these galactic outflows that at some point then mix in and recycle with this gas that's coming from what we call the intergalactic medium that then fuels the next cycle of star formation. Another way of showing that is in the following slide here. This is another simulation which is showing a Milky Way-like galaxy that's being formed. The first thing to note is that we're seeing those feedback processes like I showed earlier, right? We have these massive star explosions and these jets that are going. And what you notice actually is that if we look at around, let's go back here, at around redshift 2, which is shown up top here, this is a particularly important and active part of this galaxy's history. In other words, the redshift 2, which is what we call the peak of cosmic star formation density, it appears that just about every galaxy during this epoch was very, very rapidly forming stars. The other takeaway from this is that galaxy evolution is a messy, complicated process that has many size scales, mass ranges, and epochs that significantly affect the galaxy's properties at a given time. And in our case, we want to make sure that we account for all this mass, including the circumgalactic medium. So I've hopefully convinced you at this point that the CGM is important. Yes. So the question is, why has this been so difficult to actually pin down, right? It turns out that the CGM is actually very diffuse, so we have to rely on these chance alignments between background sources that are actually going to illuminate the gas. In other words, the CGM is so diffuse that it doesn't really emit photons very readily, so you have to use some other object to illuminate the gas. What this looks like is the following. We have some galaxy in the foreground, and around it is this diffuse or invisible to us reservoir of mass. We have some background source that's going to intersect that as we look towards the system. So what we see is this very bright source, and at a very small distance away from it, we have the galaxy that we actually care about. So what we want to do then is actually get a spectrum of this quasar, or of this background, this bright background source, and that's what I'm showing here in this dash red. What we want to do now is actually look in that spectrum and look at wavelengths that we expect there to be absorption from certain elements. And in this case, hydrogen. What's cool about this view and this particular distance that this galaxy is at is that we also get metal absorption lines. By the way, metals for astronomers are anything that's more, or any elements that are more massive than helium. Sorry. If you have questions for why that is, we can talk about it later. So, in practice, though, this is actually really hard to do. And the reason is because, again, you have this very bright background source that's right next to this very faint foreground source. It turns out, though, that you can use these objects for other means. I actually use them to put constraints on the metals ejected from massive stars, which was my second paper. It was a really good time. But there's a lack. We need to get more galaxies in this particular configuration. And so that's what that's what I've been doing with my dissertation for this entire time. I really like this acronym, so we're going to read through this together. So this is called KVSS in close, which stands for the inner CGM of QSO line of sight emitting galaxies, because we are close in to the quasars. No? Okay, I like it, whatever. I think it's fine. So what I'm showing here is what we've learned thus far about the CGM using very, very small sample of galaxies. So we have this very, very cold gas, this intermediate temperature gas, this hot gas, all of it's recycling. There's some gases inflowing, some that's outflowing, and what we get from this single sideline is some random smattering of it all. So what we wanted to try and do was actually build a large enough statistical sample to try and smooth over the stochasticity of this method. So I'd be remiss if I didn't mention what KBSS is. This is the Keck Baryonic Structure Survey, and my thesis would just not be possible if it wasn't for the basically 2.5 decades worth of work that's gone into this. So the steps for the survey are actually pretty simple. The first is to find new galaxies, and so we're using this very new instrument called the Keck Cosmic Web Imager, which is on one of the twin telescopes at Keck Observatory in Hawaii. And I'll show why this is such a big deal. But from there, we get an idea of the galaxies and the distances that they're at. The second thing we want to do is actually confirm that these galaxies are at the redshift or the distance that I'm actually claiming them to be, right? And these first two steps represent all the new data that exists, that was required for this survey. And it took a lot of work. We can then I then made use of all the images that we have in hand. So these are like literally just pictures of the night sky using different filters, different colors, where I was able to put constraints on the masses and the ages of these galaxies. And these first three steps give you the bare minimum of what you want to know about the interstellar medium of each of the galaxies. And the final part with all of this is to actually analyze the circumgalactic medium, right? Like I'm the CGM guy, right? And this is where we actually do that. And there's lots and lots of steps that we had to take to actually get there. And the final part of all this is to actually combine this analysis. That's the real utility of it all. And I'd be remiss to say one more time that, again, this is all due to the amazing efforts that have been placed before me, and all the work and all the help that I've gotten over the past few years. So, with this slide, I want to try and show explicitly why this has been so difficult. So on the left here, I'm showing a background quasar, actually the same one that I showed earlier, and this is actually where a galaxy is. And you don't believe me because you don't see it, which is the right thing to do. The reason that it's so difficult to just remove this bright object from it is because what we're really looking at is a three-dimensional object. So for every pixel that's in this image, you have a third axis, which is actually the spectrum. So it's not trivial to remove it. I spent a lot of time developing a technique to actually do this, and I'm showing on the right-hand side that, yes, we can actually recover galaxies that are this close in. So I'm showing here one of the galaxies in one, and every other source that's in the sample, we have a preliminary redshift, which is phenomenal. In other words, we have a distance for where it actually sits. We also have this extended emission here in these gray contours, which I have a student that's working on a separate aspect of this, but she's trying to put constraints on how long it takes for galaxies to go through what they call the quasar phase, but I just wanted to give her a quick shout out. I'm going to finish by showing two plots that I think really drive this work and why it's been so important to do. On the y-axis here, I'm showing the nitrogen to oxygen ratio, or you can think about it as the fraction of metals ejected from massive stars. And on the x-axis here, I'm showing the oxygen abundance, or in other words, the age of the system. We can see these two galaxies here. We have gas from the circumgalactic medium and gas from the interstellar medium, and then same thing for these other two. For this first galaxy here, this is exactly what one would expect, that you expect the interstellar medium to be more chemically evolved because you actually have star formation that's occurring there and therefore metals being produced, whereas the CGM sits in a region where there's very few metals and you're just getting enrichment from like the very first episode of star formation. The interesting thing, though, is that we have this other galaxy where it looks like the metallicities are kind of comparable, which doesn't mesh very well with the picture that I just mentioned. And the short answer is we don't really know what's going on there. So I would argue this is another reason why we need to build, or why we need to continue building this large sample and start to sample this space a little bit more. And the final thing here is looking at the survey as a whole. So we're looking at the hydrogen abundance on the y-axis here and the distance from that bright source that I was talking about on the x-axis. For those that are not in the field, the big takeaway from this plot is that there were 8 galaxies here before. Now we have 54. So the survey actually works. For those that are in the field, we're spanning 7 orders of magnitude in hydrogen abundance, which is phenomenal. It sort of shows 2 things here. First, that hydrogen is everywhere, which isn't necessarily too surprising, but that CGM does actually seem to make a difference when it comes to your selection with these objects. Okay. We're probing very, very important impact parameters, so we're probing very close into the quasar, to the actual galaxy itself, so that you can be ensured that you're looking at gas that's associated with the source. And then stuff down here, not too sure what's going on, but it's kind of fun. So I will go ahead and in here and say that during my thesis, I contributed to 3 different fields of astrophysics, which has been really, really fun. And the survey that I'm spearheading actually works. I didn't get to talk about it too much, but it turns out that the CGM at Redshift 2 is very complex, and there's lots and lots of gas out there. And so it's a good thing that we're finally getting to the point where we can account for all of it. I want to give acknowledgement to my mom, to the fam, to my fiance Tay, to my group here, Chuck Seidel and the Haze Galaxy groups, as well as Evan Kirby at Notre Dame, the Galactic Geology group. And I'd like to say that I think this is probably the first time I'm announcing this publicly, but I'll be starting a UC President's Postdoctoral Fellowship at UCLA and a Carnegie Princeton Fellowship at Carnegie Observatories in Princeton after this. So very, very thankful, and I'll take any questions.